So now we are going to use the blockMeshDict. But first, let me explain what it's going to do. What it's going to do is going to set a bounding box. So this bounding box needs to be bigger than our actual computational domain. So it would be like drawing not a rectangle but a cube that encloses our domain, but it needs to be bigger. It doesn't matter, it doesn't need to be much bigger, but just a bit. For example, let's take a point here using a line here. So this coordinate here, this corner is located at the coordinates 5, 1.6 and 0.52. So we will need to make a mesh with the blockMeshDict that is a little bit bigger. So let's start doing that. We are going to create a new folder that is going to contain our simulations. So in here we are going to create first a simple case that is going to have a cell size of 1 centimeter. So we call this folder 0.01 centimeters, and we call this, let me add blockMesh. So we are just using blockMesh here. So we need to have a template from previous cases. So we let me find some. For example, I have here a case that I've worked with before. So inside that directory we are gonna have the 0 folder, the constant folder, and the system folder. Don't worry about the one that I deleted. I'm gonna show you how to create that later. So we are supposing that we don't have anything, so we don't have any mesh created and anything. These are properties of the model, not related to the mesh. So in here in system we have the blockMeshDict that we're going to use. What else is necessary? The control dict is necessary, and this one here not now. We use them, but for the simulation itself. Set fields is related to the geometry, but we are not using that. We are using blockMesh, SurfaceFeatureExtractDict, and the snappyHexMeshDict. That is all we're going to see in this video. So as I told you, we're going to start with the blockMeshDict. We want to start from the beginning. So we're going to set our limits, the limits of our domain. So here we have the outermost corner, I guess, that is located at the coordinate 5, 1.6 and 0.52. So as I told you, we could use here for the x-axis an x-max of 5, but we need to make our bounding box a little bit bigger, so we don't have any trouble. So let me put here, let me add, as our mesh is 1 centimeter, let's add 1 centimeter to each side. So in the y-axis we have 1.6, so we put here 1.61. As well in the z-axis we have 0.52, let's put 0.53. So that is the first part of the blockMeshDict. Let me put this here and let me open my navigator. The one to show you is the blockmesh.png. documentation, we search for BlockMesh, and as we can see, this is the way it works. We are just creating one big cube, but we need to follow the convention that is established here. As you can see, we have eight vertices that are going to define our cube. So first we need to set the coordinates of those vertices in such a manner that it is easy for us to understand. So we are going to follow this order, okay? 0, 1, 2, 3 in a counterclockwise manner. So we start with the 0 vertex. That is going to be, let me erase everything. So we do everything from the beginning. So okay, we don't have anything. So our first coordinate is going to be the easiest one. It will be 0, 0, 0. The next one, we are moving along the x-axis, so we will have 5.01, and here we would have 0 and 0. So we're continuing. We have the 2, 5.01. This would be 1.61, and this would be 0. So the third one would be 0, 1.61, and 0. So the following are going to be the same for the x and for the y axis, but for the z axis is going to change. It's going to be, in this case, 0.53 in all those vertices. So we are done with that part. So what follows is to define these blocks. In this part we are only defining the vertices, so we need to combine them together so we can make sense of this sketch. So we erase this line, so we do that from the beginning. First we need to set the order, as I told you, in a counterclockwise manner. So we start with the 0, 1, 2, 3. As we follow that order at the beginning, it follows that it is in order in this line, and then we go to the upper phase. That will be 4, 5, 6, and 7. So it's pretty easy if you follow that order from the beginning. So in the next part, we are defining the number of separation that is going to that we are making in each axis. So for example, we said at the beginning that we are using a 0.01 meters cell size, or that means 1 centimeter. So what I do is I take the calculator and I put this number 5.01, and I divide it by 0.01. That's the mesh size that we want. So in this case, this is a pretty simple division, but it could get complicated. So for the x-axis, we would want 501 divisions. For the y-axis, we would want 161. And for the z-axis, we will want 53. Okay. Simple grading, what this means is that these divisions are going to be equal for all the divisions are going to be equal, divided equal. So as I told you at the beginning, we are designing, we are constructing an structured mesh. So every cell is going to be a perfect cube. So we leave this here, 1, 1, 1. In this section edges, we are not defining anything. We follow by defining the boundaries and setting the names of the boundaries. So this cube that we have defined here in this block has multiple faces. So we need to define what type of faces these are. So as this is this is a sketch. This is the mesh we are going to start from, and we are going to subtract from the surfaces we created with Blender. So the type, it doesn't matter, but then let's set it empty and define. Here we define the different faces we have. For example, the first face, the bottom one, would be 0, 1, 2, 3. The next one, the upper face, would be 4, 5, 6, and 7. The next one would be 1, 5, 6, 2, 0, 4, 7, 3, 0, 1, 5, 4, and finally 3, 2, 6, and 7. So we have defined everything we need to run our blockMeshDict. We have defined the limits of our domain, the vertices we need to create, the blocks, how this block is going to be divided, and we have set the type of faces we have. So we can save this. We can save this file, and we can go back to our folder, case folder. We can type here WSL. So we have the Ubuntu terminal. So now we are here. We run blockMesh, and if everything is okay, it would run, but there seems to be a problem. So this error reads file name call for invalid file name. Well, this happens when there is a problem with the name of maybe a folder. So let me check. Yes, I see the mistake. So we defined at the beginning our folder that was called 3D Mesh. The problem with this is that there is a space, and for some reason OpenFOAM doesn't like spaces. So we need to subtract this space and replace it with a underscore, let's say 3D Mesh. I cannot change the name because I have this file open, I guess. So I close it. I don't need to save that. Let's try again. Nothing. So I cancel this. I close this terminal. I try again to change the name, and now I can change it. So now we have changed the name. So let's go back inside simulations, our case directory. So we enter again to the Ubuntu terminal, and we try now to run blockMesh. And now, as you can see, it's running. It's creating the cells as we want. Every cell is going to be 0.01 meter in every axis. So let's wait a minute. Okay, it finished. So let's check the results of this. So to open this mesh, we need to install paraView. If you don't have it already, you can just search for paraView in your navigator and search for this option, download paraView. You can download the latest version for your system. Version 5.11 is the latest one. If I'm not mistaken, you can just use in as you can see, in Windows, Linux, and Mac OS. The installation process is pretty simple, but I'm not going to get into it. So once you have installed this, you run this command. Well, let me show you. You can open your case, opening paraView, file, open, you search for your folder. We have it on desktop, 3D mesh, simulations, and you go to the system folder and you change here files of type of files, and set it to all files, and open the control dict. Okay, and you search here for OpenFOAM Reader. So as you can see, this doesn't look good. Wait. What happened here? We did something wrong. So probably defining our control, our blockMeshDict. So let me check. Yes, here's the mistake. So we need here 5.01, and this should be, we save this, we go here again and we run blockMesh. You don't need to delete it, the folder that was created, because it's going to overwrite it. So we wait a moment. Okay, finish. So let's reload this mesh. So we made a mistake. So we right click here and we reload the files. Well, and now that is correct. But before we talk about this, I want to show you a way to open this control dict file faster. So let's close this, and here in the terminal you can type this command, touch, and the name of the file that is going to open our case. So I like to call this open.foam. We hit enter and we go back to the file case file, and we can see that this file has been created, open.foam. If we click there, maybe for you it's not going to be set to be opened by paraView, but you can set that going to properties and opens with, and you change it to paraView. So once you click that, the case opens directly. So now we have our domain. But what is this? This is a box. This is not the surface we want, the geometry we want. What we want would be, let's open that, the STL we created before. We created a capped STL. Let's set the opacity of this to this to here. So as you can see, the geometry we want is inside this the geometry we created with blockMesh, and as I told you, we had we did it a bigger we created a bigger cube so that it encloses the geometry. Okay, that is important step, so we don't have problems when we are using when we use SnappyHex mesh layer. So okay, let's close that. We are done with the blockMesh part. So what we need now is we are going to use the following command, the surfaceFeatureExtract command. So for that, we need to set in the constant folder, we need to have a tree surface folder. Don't worry about this polymesh folder. It was created when you run the blockMesh command. But this tree file surface folder is empty. It doesn't have anything. But we are going to put there is the STLs that we created in Blender. So we copy them and we paste them in the tree surface. So what is next? We go back to the system folder and now we open the surfaceFeatureExtractDict. We open this on Notepad. Let's set this to C++. Okay. What this does, this reads those STLs we put in the try surface dict. So the structure is pretty simple. We have for every STL we need to create this. So we need to create an atmosphere.stl, and this description here is going to be the same for all. So for example, this include angle is important to be set to 180, so it includes all angles of all features. So I always set it to 180, and we do that. Let's put this here, and in our case directory we pasted 6 STLs. So we need to define here 6 STLs. So we define first atmosphere STL, bottom STL, inlet STL, outlet, sidewalls, and wall 1. That would be 6 STLs. So we save this and we go back to our terminal, and this part is pretty straightforward. So we type the command surfaceFeatureExtract and we hit enter. It's pretty fast, so we are done with that. So what that command did, it created these new files that are in the image file format, and it also created this new folder called extended feature edge mesh. So those files are necessary for our next step, that is the snappy hex mesh step.